Welcome back. So, this is lecture 5 in this course and we are discussing random variables. So, I introduced random variables in the previous lecture, at the end of the previous lecture. And what we saw was that, well, in particular situation where your outcomes are categorical, for example, when you are tossing a coin 2 times or 3 times, then the outcomes you have, basically your sample space, contains these categorical outcomes: head head, head tail head, and tail, right? So, in this situation it is very difficult to define a probability assigner function on this sample space because it contains these categorical outcomes. So, if you define a probability assigner function on this, you will need 3 or 4, basically 4 rows containing theta probability for each possible outcome, right? So, it is very difficult. So, the only way we can avoid this problem is that we transform this categorical space into a well behaved numeric space, right? And that is where random variables comes in, right? So, random variable is a function. So, let us say this capital X, we denote random variables by these capital letters. So, random variable is a function that maps your sample space to another space omega x, which would have numeric values and would be convenient to define any probability assigner function of this. And what this function does? Well, you can make it do something that transform these on numeric space. So, let us say you define this x in such a way that it counts the number of heads in each member of your sample space. So, what are the number of heads in the first member? HH 2. So, it would map it to 2. If you take HT, then it would map it to 1. TH, it would map it to 1 because there is one head. TT, it would map it to 0. Okay. So, a random variable is a function which maps your sample space to another space omega x. Okay. So, random variable is a mapping from omega to omega x. What is omega? Your original sample space. Omega x is another numeric space, right? What is x? It is a function that maps omega to omega x. Now, you can define x in whatever way you want. It can depend on what kind of research question you are interested in. You can also define x as something which counts the tails or the number of tails in your outcomes. Now, interestingly, this is an example where it is very straightforward to see why we require random variables, why we require such functions that transforms a categorical space to a numeric space. And what is that? Well, we need these random variables so that we can define our probability assigner functions on a numeric space rather than on categorical space. How? Let us see. So, actually, for the same problem, if you would have to define the probability assigner function on omega on the original sample space, this is what you would have to do. We have done this earlier as well in the previous lecture. So, this is what we end up doing, that the probability assigner function would be defined in this way: theta 1 if W is HH, theta 2 if W is HT, theta 3 if W is TH, and 1 minus theta 1 plus theta 2 plus theta 3 if W is TT. So, this is what you would do if you are defining this probability assigner function on omega. But if you have to define this probability assigner function on omega x, you do not need such complicated function. Why? So, let us say x belongs to omega x. So, basically any element in omega x. So, we can define now probability assigner function in this way: f of x theta equals to 2cx, 2 chooses x, theta to the power x, 1 minus theta to the power 2 minus x. So, I have defined a probability assigner function using a very simple formula in a single line. That is very convenient. But does it work? Does it satisfy 3 axioms? Let us see. So, what axiom that needs to be followed here? axiom that needs to be followed is this: probability of E1 plus probability of E1. Basically, this is the constraint that it needs to follow based on 3 axioms. Probability of E3 plus probability of E4 should be equal to 1. So, that needs to be followed. Well, let us see if this function follows this. So, based on this function, what is probability of E1? Okay. What is probability of E1? What is E1? E1 is an elementary event containing HH. Okay. So, what is probability of HH based on this function? So, HH is actually corresponds to this outcome 2. Basically, a value of x is basically 2 here. Okay. So, this would be f of x equals to 2, okay, and theta. So, if x is 2, then 2 chooses 2, okay, theta to the power 2, 1 minus theta to the power 0. So, this would turn out to be theta square. Okay. Is it correct? Yes. What would be probability of E2? X equals to, for E2 the event is HT and the value of x would be 1. So, this would be 2C1 theta square 1 minus theta to the power 1 minus theta to the power 1. So, it would be 2 into theta into 1 minus theta. Okay. What would be P of E4? E4 is what? TT. So, basically x is 0. F of x equals to 0 and theta. So, that would be 2C0 theta to the power 0 1 minus theta to the power 2. So, it would be 2 into 1 minus theta whole square. So, that is 2 into 1 plus theta square minus 2 theta. So, 2 plus 2 theta square minus 4 theta. Okay. All right. And what would be E3? Probability of E3. So, E3 would be same as E2. So, that would be 2 theta into 1 minus theta. Okay. So, this is what we are getting so far. So, probability of E1 is theta square, E2 is 2 theta 1 minus theta, E3 is 2 theta 1 minus theta, E4 is 2 plus 2 theta square minus 4 theta. What happens when you sum them up? You take summation of all these 4. Okay. So, let us take their summation. When we take their summation, what we get is theta square plus 2 theta minus 2 theta square plus 2 theta minus 2 theta square plus so here it won't be a 2 in E4 because it's 2C0, so it will cancel out. So, it would be just 1 minus theta square minus 2 theta. So, 1 plus theta square minus 2 theta. Okay. All right. And also this would go away because now when you apply this applies these 3 axioms to this sample space omega x, you need to apply 3 axioms on this sample space omega x. So, what are the possible values omega x can take? There are 3, 0, 1 or 2, right. There are 3 possible values omega x can take. So, that means probability of x equals to 0 plus probability of x equals to 1 plus probability of x equals to 2, okay, will be equal to 1. So, that is the constraint it should satisfy. Okay. So, probability of x equals to 0 is given by theta square, x equals to 1 is given by this 2 theta minus 2 theta square, and probability of x equals to 2 is given by this 1 plus theta square minus 2 theta. So, when we sum them up, so these will cancel, the theta term will also cancel and you will get 1. Okay. So, it satisfies the 3 axioms for this sample space omega x, considering this is the new sample space, right. So, what we did here was that we defined so let us just revisit. So, this was our original sample space, and we defined a random variable x, which is a function which maps omega to omega x in such a way that omega x would have these values now 2, 1, 0. So, it counts the number of heads in the outcomes in omega, right, and you can think of the mapping. So, this maps to 2, this maps to 1, this maps to 1, this maps to 0. Okay. Now, we define a probability assigner function on this new space omega x. And what probability assigner function we have defined? It is 2c x theta to the power x 1 minus theta to the power 2 minus x. Okay. And the property this function should satisfy, the constraint this function should satisfy, because it is a probability assigner function, is this, that probability of x equals to 1 plus probability of x equals to 2, basically all the elementary events in this space omega x. Okay. So, probability of summation of probability of elementary events is equal to 1, and we check that when we plug in x equals to 1 here, what we get is we get 2 into theta 1 minus theta. When we plug x equals to 2, we get theta square. When we plug p x equals to 0, we get 1 minus theta whole square, and when we sum them up, the theta terms go away and we end up getting this is equal to 1. Okay. So, our constraints posited by 3 axioms of probability are satisfied here. Okay. So, this is what we have achieved. We have reduced this very complex probability assigner function into a very convenient one. Why? Because we transformed this sample space to a numeric space omega x using a random variable x. Okay. So, that is the utility of a random variable, that now you can define probability assigner function on a numeric space. Okay. So, this concept of random variable is very fundamental to inference, and the reason is this, that we always define the probability assigner function on the values of the random variable. Okay. So, consider any experiment. The experiment has a sample space omega. Okay. For every experiment, you need to define a random variable depending on whatever you want to do with that experiment, right. So, you will define a random variable x which transform omega to omega x. Now, you define a probability assigner function f of x theta on the values of this random variable omega x. And what this function gives you? It gives you probabilities for your events in the event space. Okay. That is how this whole workflow works, right. So, this is how you make assumptions about what is the underlying generative process behind your data. So, once you get data, you infer what is the value of theta that would have generated this data given this function f. Okay. And then by extension, you try to infer what is the true generative process, and you can compare it with another competing function, let us say g of x phi. Okay. So, whatever competing functions, competing probability assigner functions you would have, they would all be defined on this, on the values of the random variable. Okay. So, that is the utility of random variables. So, this is very fundamental to inference. So, everything we do it on the values of the random variable. Basically, all the assumptions, all the probability assigner functions we define them on the values of the random variables. Okay, a question. So, random variable is a function, right. So, for a function you can define your domain and codomain. So, what is the domain and codomain of a random variable? when, let's say, you're tossing a coin 2 times. For a 2 times coin toss experiment, okay, what is the domain and codomain of your random variable? Because it's a function, so you can define its domain and codomain. Just think about it. Domain is the set of all the possible values that this function can take as its input, and codomain are the set of all the possible values that this function can give as output. Okay, so just think about it. What would be domain and codomain for this example, for 2 times coin toss example? Okay, so this is a little exercise for you. All right. So we saw a straightforward utility of a random variable when the outcomes that you are interested in are of categorical type. For a coin toss example, or when the participant has to recognize whether the string on the screen is a word or not word, they will give responses using yes, no, and they would recognize whether it's a word or not, whether it's a proper meaningful word or not. What are the responses you are recording? Yes or no, right? These are categorical. So you can, in the same way, you can apply the random variables here. You can define a random variable x such that which maps your sample space to another space omega x. What is omega? Y or n. You can define the mapping in such a way that if the response is y, the value of random variable is 1. If response is n, then the value of random variable is 0. Now you can go ahead and define a probability assigner function on values of the random variable. So let's say you can define a probability assigner function like this: f of x theta equals to theta to the power x 1 minus theta to the power 1 minus x. So you can define a probability assigner function like this. Fine. So this is straightforward. So whenever the outcomes you are getting are of categorical type, like yes, no, true, false, head, tail, tail, heads, right? Or let's say for an experiment where you are recording how many road accidents occur in a day in Kanpur. Okay, so you are recording how many total road accidents occur in a day in Kanpur. So the values could be, let's say, 30, 35, 24, 7, like this, right? So in this case as well, you have basically discrete values, although these are not categorical now. Okay, categorical in the sense they are not these non-numeric values y n, they are still categorical, but they are not non-numeric. These numbers mean something, right? Are not categorical in the sense the y and n is. These are actually numeric values, so that is not the problem, and they mean something, right? 30 means there are 30 road accident, 35 is greater than 30, so they are not categories like y and head, tail, head, right? So these are not categorical responses, these are numeric responses, although they are discrete. Okay, so what you would do in this case? So let's say we are studying how many road accidents occur in a day in Kanpur, right? And the outcome that we want to record is, let's say, just for one day. Okay, so that doesn't matter. Okay. So what are the possible outcomes? So you can record anything. So let's say you decided that tomorrow I will record the number of road accidents that would occur in Kanpur. Okay. Now this number could be anything, right? It should be, of course, less than the population of Kanpur, but this number could be anything. So all those are possible outcomes in your experiment. So if I ask you to define the sample space, what it would look like? Well, it would be set of all natural numbers, including 0, all whole numbers. So let's say 0, 1, 2, 3, right? It's 1,000, so on. But they all has to be integers, right? So basically, it's a set of non-negative integers, but less than population of the Kanpur, right. So, that is your sample space. These are all the possible outcomes that can occur, basically all the possible values that you can record tomorrow, right. Now, how would your random variable look like here? So, random variable, remember, it is a function that maps values in your or the elements of your sample space to another space omega x, which is well behaved and numeric. But this is already numeric and well behaved. So, you do not need to worry about this, but you should still define a random variable, because we will follow this principle that whatever probability assigner function we are going to define, we define it on the values of the random variable. So, what you can do in this situation is that you define a random variable x in such a way that it has exactly, basically it maps omega to omega x, which is same as omega. So, basically it is mapping to exactly same values, right. So, if omega is 0, 1, 2, 3, 4, omega x also has 0, 1, 2, 3, 4, and mapping it like this. Okay. So, this works for us, no problem in this. So, in fact, you can write that x of omega is equals to omega, where omega is an element of this sample space. Okay. However, if you are interested in something else, let us say you are interested in categories like you are interested in studying that whether number of road accidents are less than 10 on a particular day or more than 10 on a particular day. Now, you have two categories, less than 10 category and more than 10 category. In that case, you will define another random variable which will have a value 0 if number of road accidents is less than 10, or 1 if number of road accidents is greater than 10. So, you can actually make use of these random variables in any way you want. So, basically in this case, let us say you define two categories. Such that, let us say random variable y, to make a distinction I will call it y. So, if values are 0, 1, 2, 3 up to 10, it will map all of them to a value 0, and if it is greater than 10, all these values, they will be mapped to 1. Okay. So, what 0 indicates? Low accident rate, 1 indicates high accident rate or high accident number. Okay. So, 1 is for when number of accidents is greater than 10, 0 when number of accidents is less than 10. This could be useful for a particular theory, right. So, that is not what our main problem is here, right. What we are just showing is that the random variable can be used to even go from a more numeric space to basically go from a more distributed space to create categories of this sort 0, 1. But of course, whatever it would create should be numeric. So, this is fine. Going back to number of road accidents example. So, here our sample space is already numeric and well behaved. So, we are just mapping them to exactly same value 0 to 0, 1 to 1, 2 to 2, right. So, basically you are defining a random variable such that it takes exactly same value from omega and gives exactly same value in omega x. So, whatever probability assigner function we are defining on our original sample space, right. But of course, we say that we are defining them on values of the random variable. So, you still need to define a random variable. Okay. But the random variable is such that you are exactly mapping the same. So, omega and omega x are basically same. But think about a situation, let us say in this word recognition experiment, you are not interested in whether they are producing yes or no response, but let us say you are interested in recording how much time do they take to recognize this word, whether it is a proper word or not. Let us call this reaction time, recognition time. So, how much time do they take to recognize this word? Okay. How much time can they take? Well, it could be anything, let's say 50 milliseconds or 70 milliseconds or 100 milliseconds, 200 milliseconds, 800 milliseconds, right? Even 1500 or 2 seconds. It's very rare to have it beyond 2 seconds, but it could be anywhere between, let's say, 50 milliseconds to 2000 milliseconds, right? And also it could also be, let's say, 55.55 milliseconds, right? So what is your sample space here? What are all the possible outcomes you can get? What are all the possible recognition times that you can get when someone reads this on a screen, when someone tries to recognize this word on a screen? So it turns out that the possible recognition time you can get could be, let's say, anywhere between 0 and plus infinity, right? So possible recognition time could be any point on this number line between 0 and infinity. So what kind of sample space is this? Right? So omega is, let us call this, it's a set of all positive real numbers. This is your sample space now. It's a set of all positive real numbers. It could be anything, any point on this real number line. Okay. Now this is interesting because now your sample space for the first time in the whatever examples you have taken, it's not discrete anymore. Okay. Even in the road accident example, what you are getting were discrete outcomes. So road accident could be either 1 or 2 or 3 or 4, like that. Okay. Now we do not have discrete outcomes anymore. This is called a continuous sample space, because the possible outcome could be anywhere on this real number line between 0 and infinity. Okay. So what does this imply? Would it be any different for inference? Well, let us see. So of course, as I said, that you will always need to define a random variable even if your sample space is already numeric. So let's define a random variable x such that it does not make a difference. So x of omega equals to omega, where omega belongs to your original sample space, right? So basically, this omega x and omega are same set. Okay. So you defined a random variable x in such a way. Okay, but now let us apply probability axioms to derive what kind of probability assigner functions you need to define here. Now this part gets tricky. Let us derive from the first axiom. Well, first axiom says that any event in the event space should be greater than equal to 0. Okay, but what is an event here? And let us start with what is a possible outcome here. A possible outcome is any point on the real number line between 0 and infinity. So in a particular trial, you would record one reaction time, or in a particular experiment, you would record one recognition time, which could be 50 milliseconds or 75.5, or could be anything, right? So that could be any point on this real number line. Okay. But what would be an event? What is an event? So event is a possible subset of your sample space. What is the sample space? All real numbers between 0 and infinity, basically this whole line. Okay, this whole line, this is your sample space. What would be a possible subset of all these real numbers? Well, there could be two kind of possible subsets. One is this, that any point, okay, let us call them v1, v2, so on, any point on this real number line would be a subset of omega. Okay, it would be subset of set of positive real numbers, right? So any point on this real number line would be a possible subset. So those are all events. So any point on this real number line is an event. Okay, that's one kind of event. What could be another kind of event? any segment, basically any interval on this real number line is also an event, because it's a subset of the set of positive real numbers. So, if I say that the interval between 50 and 100, okay, this is also an event, and it's a subset of your sample space omega. Yeah, it's a subset of your set of positive real numbers. Okay, what does this indicate? This interval between 50 and 100, that this is an event such that the recognition time would occur anywhere between 50 and 100. Okay, so a probability assigner function should be able to assign some probability to this event, that what is the probability of obtaining a reaction time between 50 and 100 given a particular probability assigner function. Okay, so these are two kind of events that you can think of for a continuous sample space. One type of event is points on this real number line, another kind of event is intervals on this real number line. Okay, now let us think of second axiom. Second axiom says that at least one of the elementary event must occur. What are the elementary events here? Is this even? Is this an elementary event? No, it contains infinite values between 50 and 100. It's not an elementary event. Is V1 an elementary event? V1 is a point on this line. Yes, V1 is an elementary event. So, in fact, elementary events are all the points on the real number line between 0 and infinity. All the points. Okay, how many points do we have? Infinite number of points, right? How many points we have between V1 and V2? Infinite number of points. Okay, all these points are elementary events. So, let us apply second axiom to these points. So, let us say the first point is V1, second is V2, and there would be infinite number of points between V1, V2 as well as let us say between V3, okay, union V4, right. So, probability of their union would be equal to 1. Okay. By the way, these are infinite number of points, V1 to whatever Vn, so like infinite number of points, and the probability of union of all those events is equal to 1. That is what the second axiom says. Now, let us also apply the third axiom. Third axiom says that for mutually exclusive events, probability of their union is summation of individual probabilities. Now, all these points on this real number line, they also constitute mutually exclusive events. Okay, because these points do not have anything in common, these are individual points, these are elementary events. So, when you apply this, so this whole thing, probability of V1 union V2 union V3, okay, this would be equal to probability of V1 plus probability of V2 plus probability of V3, okay, so on. Okay. Now, this V1 union V2 union V3, all this is equal to 1 based on second axiom. So, you can write, basically it is the same result as we have derived before, but just that elementary events are now very different. So, probability of V1, and there would be infinite number of elementary events between V1 and V2, probability of V2 plus probability of V3 is equals to 1. Okay. So, this is the constraint that must be satisfied by any probability assigner function. But how is this possible? How it could happen that summation of all these probabilities is equal to 1, and also that these individual probabilities are greater than equal to 0. Okay. Why it is difficult? Because there are infinite number of such elementary events, and the summation of probabilities of infinite number of events is equal to 1, given that each probability should be greater than equal to 0. Only way this could be possible is that each probability tends to 0. Otherwise, this principle, this particular result won't hold. Okay. So, what it implies is that probability of any point value, okay, in a continuous sample space has to be equal to 0, where V1 is a point value, it is an elementary event, it belongs to your sample space omega. Okay. So, probability of any point value in your continuous sample space is equal to 0. So, cannot assign a non-zero probability to point values in your continuous sample space. Then what the probability assigner function would do? Well, it can still assign probabilities to intervals, these another kind of events. So, let us say E1 is interval between 50, 100, E2 is an interval between, let us say, 100 and 150, right, so on. So, it can still assign probabilities to events E1, E2, E3, which are basically intervals containing infinite number of values between certain bound, let us say between 50 and 100, right. So, although probability of 50 will be 0, probability of 100 will be 0, but probability of obtaining a recognition time between 50 and 100 would be non-zero. So, this can be assigned by a probability assigner function. Okay. So, the nature of probability assigner function is going to be very different for these cases. Okay. Which cases? For continuous sample space. That is why we make this important distinction between discrete sample space and continuous sample space. Okay. So, the random variables that we use to define probability assigner functions on discrete sample space are called discrete random variables. So, basically random variable associated with discrete sample space, and random variables associated with the continuous sample space are called continuous random variables. Basically, you can say the random variables which have discrete values versus random variables which have continuous values, right. So, you will hear these terms, discrete random variables and continuous random variables. And the classic examples, you might have heard about them. The examples of discrete random variables are, let us say, a coin toss, head tail, that kind of example where you count the number of heads in n number of coin tosses. Okay. Number of heads in coin toss, number of road accidents, right, number of correct responses in a particular experiment, right. For example, this is called a binomial random variable. This can be given by a binomial random variable, this can be given by a Poisson random variable, this can be given by a binomial random variable. Continuous cases are, let us say, reaction time observed in an experiment, it is continuous, heights of individuals observed in a population, marks in a class, right. So, for example, this can have a normal random variable, this is a normal random variable, RTs could be a log normal random variable, right. So, we will see these common examples, all these are different types of random variables, or you can say different types of probability assigner functions, right, that you can use to define assumptions, okay, about a particular set of observations or about a particular experiment. So, we will see these common types of discrete random variables and continuous random variables in the next lecture. Alright, so that is it for this lecture. In the next lecture, next week, we will start with different types of discrete random variables and continuous random variables. So, we will take some examples, the most common examples that we will be using in this course. Alright, thank you very much.